Hi, third graders. I'm back again to do some more work with you guys for our week 4 of remote learning. Or no, week 5. I have to double check. No, week 4 of remote learning. The first week we didn't really do a lot of online stuff. It was just more kind of like getting to know you stuff. So I'm going to be doing 2 more math lessons for this week. And I hopefully will also have a reading lesson for you as well to watch. So hopefully there should be 3 videos for you to watch for this week. And then peppered in will be a bunch of other things to do. And I hope things are going well with you. I hope I'm not confusing you with anything. I hope you will reach out to me if there's any extra resources you need, or if there's anything that you're not understanding. I hope you will reach out and let me know what I can do to help you some more. All right, so we are going to get ready. I would like you to make sure that you have your lesson number 4 out. It starts on page 17 for math, and we're going to be understanding the commutative property of multiplication. So I'm going to move my camera down, and it will be upside down for a second, but I'll get it to the right direction. All right. Okay, so lesson 4, understand the commutative property of multiplication. So after this lesson is done, you are going to be able to use the commutative property of multiplication to write related multiplication equations. And this big word, what this big word means, commutative property, it just means when you multiply in one direction, you can multiply in the other direction as well. So for example, when we add, if I do 4 plus 2, I'm just going to show that to you up here. If I do 4 plus 2, I know it equals 6. And I know I can also write 2 plus 4, and I'm going to get the same answer, right? I'm going to get 6. So that's what this big word means. It just means whatever direction, whatever place I put these digits in, for addition and for multiplication, it doesn't matter the order. I'm going to get the same answer. Okay, so when we add, we know we could do 4 plus 2 equals 6 and 2 plus 4 equals 6. Okay, so now when I go to multiplication, I'm going to be able to do the same thing, and we're going to explore that. I'm going to show you why that works. Okay, so in Spark Your Learning, Andy designed the game board shown. Suppose you are designing a game board. The game will have 21 squares. The squares will need to be in equal rows. So let's think about this for a minute. We need to have equal rows, and we know we need 21 squares. So we need to kind of problem solve and figure out, well, how many squares are going to be in each row? Well, I know, or I'm going to start counting. I'm going to start with 3, only because I know that this is an odd number. And if this is an odd number, I can't do 2. I can never use the number 2 to make my rows with an odd number, because 2 can only go into even numbers. Okay, so I'm just going to try 3 and see how this works. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and it worked out. So I'm able to do 3 rows. And then how many rows are in, or how many squares are in each row? 1, 2, 3, 4, 5, 6, 7. So I have 7 squares in each row. So this tells me that I can have 3 times 7, and that is going to equal 21. Now I need to see if I can do it in a different way because it wants us to show that we can show 2 different game board designs. So I could have 3 rows with 7 squares in each row. So could I do it in the other direction? Could I have 7 rows, with 3 in each row? So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. And remember, I needed 21 squares. So I could also have 7 rows. Remember, rows go across with 3 squares. Oops, sorry. Getting ahead of myself. 3 squares in each row. So for this one means 7 times 3 equals 21. So in either direction I write this multiplication problem out, I'm going to get the answer 21. So I can either have 3 in the row section and 7 squares in each row, or I could have 7 rows with 3 squares in each row. And that's going to get me 21. So now, let's turn to the next page. And let's do some more practicing. So now Toby is designing this game board. We can see this game board over here. Nita notices that she can design a different game board with the same number of squares by turning Toby's game board. How would a turn of Toby's game board look? Describe how Nita can arrange the squares in equal rows to show a turn of Toby's game board. Well, let's see. How many rows does Toby have right now? Toby has 1, 2, 3, 4 rows. And how many are in each row? 1, 2, 3, 4, 5. So there are 5 in each row. So if Nita turned, if Nita turned his game board, then we would have how many rows in the game board? Well, if we turn it, we're going to now have 5 rows with how many squares in each row? Well, we would have 4 squares in each row. So she would just be turning it, right? She would take his board and just turn it. So it would be like this, right? We would just turn it. So we would have the 5 rows and the 4 in each row. So let's show that in picture form. So we know we need 5 rows. 1, 2, 3, 4, 5. And I want 4 squares in each row. And then I'm just going to fill in the rest. So that way I have my 5 rows and my 4 squares in each row. So I have my 5 rows going across, and I've got, make sure I've got 4 squares in each row. So let's think of the multiplication equations that we could write to model the original game. So Toby's original game had 4 rows and 5 were in each row. So total number of rows, he had 4 rows. Number of squares in each row, he had 5 squares in each row. So number of squares in all, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Or we could count by fives, right? 5, 10, 15. Oh, no, I'm sorry. I'm going in the wrong direction. 5, 10, 15, 20. I apologize. That was my mistake. So we have 20 squares all together. So if Toby's model looks like this, 4 times 5 equals 20, what model could we write by turning it when Nita turned the game board? Well, Nita turned the game board to have 5 rows with 4 squares in each row, so we have the same number of squares. This time we would count by 4, 8, 12, 16, 20. All right, page 19. I feel like I have this a little bit closer so we're not seeing the whole page, or most of the page at a time. There we go, that's a little better. All right, so Katya is designing a rectangular game board. One version of her game board is shown. Katya wants to see if there is another way to arrange the board. Show another way Katya can arrange her game board using equal rows. So she originally, this is her first game board, right? 5 rows with 3 squares in each row. What would we do to make a new game board? I hope you're thinking that we're going to turn it, right? We're going to turn that game board. So instead of 3 squares in each row, we're going to do 3 rows of the squares. And then how many squares will we put in each row? If we're going to do 3 squares in the or 3 rows, we're going to have 5 squares in each row. And I'm going to fill in the rest of my game board. Like so. So what multiplication equation could we write to model each of the game boards? Well, this first game board, we have how many rows? We have 5 rows. And what are we going to multiply our 5 by? I hope you said 3. So 5 times 3, let's see, what does 5 times 3 equal? 5, 10, 15. 5 times 3 equals 15. The other game board that we can, or other multiplication equation we can do based on the second game board is we have 3 rows times 5 squares in each row. And does it equal the same thing? Let's see. 3, 6, 9, 12, 15. Sure does. So it doesn't matter which one of these I put first, right? As long as I do the same digits. So 5 times 3 equals 15, or 3 times 5 is going to equal 15. So what do we notice about the factors in the 2 equation? And then what do we notice about the product? This, remember, is a factor, and this is a factor, and your answer is the product. So the 2 digits that you're multiplying together are the factors, and your answer is the product. So we notice that the factors, the numbers are the same, we're just putting them in a different order. So the factors are the same. They are in a different order. Right? This first one, we have the 5 first and the 3 second. In this multiplication equation, we have the 3 first and the 5 second. So that's what we notice about the factors. What do we notice about the product. Sorry, I'm going to focus this again. It's kind of, yeah, there we go, that's better. It's just a little blurry. I apologize for that. So what do we notice about the product? Well, I have a 15 here and a 15 there. That tells me that the product is the same. So the products are the same. They don't really give you a lot of room to write this in. I apologize. So our factors, even though we have the same factors, we can put them in a different order to get the same product. And we can do this with any pairs when we are multiplying, any two digits when we are multiplying. So let's check for understanding. Let's see if we understand what we're talking about. Lamar's game board has 5 rows with 6 squares in each row. Ruby's game board has 6 rows with 5 squares in each row. Do their game boards have the same number of squares? What do we think? Well, if I have 5 rows, Lamar's got 5 rows times 6 squares. If I count by 5 6 times, 5, 10, 15, 20, 25, 30. And then if I have 6 rows with 5 squares, I'm going to count the same way. If I'm counting by 6s, 6, 12, 18, 24, 30. So do their game boards have the same number of squares? Yes. And then explain. So why? Because the factors are, are the same, just in a different order, right? They're the same factors. I have a 5 and a 5 and a 6 and a 6. They're just in a different order. I have 5 times 6 in the first problem and 6 times 5 in the second problem. But look at, they both have the same product. So the factors were the same. They're just in a different order. All right, so let's practice. I know this says on your own, but I always like to do it so that way you could pause right here if you want to pause the video and try this on your own, and then come back to the video to check your answers, or you can do it right along with me if you're still a little unsure or you want a little more help. But this is a great spot to pause for a second, do this one page on your own, and then come back. So on your own, model with mathematics. So we can see we've got a picture frame here with some pictures in rows, and then there's some certain number of pictures in each row. So a frame can be hung 2 different ways. One way shows 3 rows with 6 photos. Is that what this shows? 1, 2, 3 rows, right? With 1, 2, 3, 4, 5, 6 photos in each row. The other way shows 6 rows with 3 photos in each row. Now we don't have that picture, but we know we could take this frame and go whoop, and turn it this way. Now we have, oh, excuse me, I apologize. Now we have 6 rows with 3 pictures in each row, right? If we just turn it. So if we're going to keep it in this direction, so that way we can do our writing. So we're going to write equations to model the 2 ways the photos can be shown. And then we need to show how many photos there are. So the first way was 3 rows with 6 photos in each row. So I know that I have 3 rows times 6 photos. Well, what does that equal? Well, let's see, 6, 12, 18. And the second way is 6 rows with 3 photos. 6 times 3. So if I count by 3, 6, 9, 12, 15, 18, if I've got 6 of them. So I have how many photos? 18 photos. Because I need to answer all parts. It wants us to write equations to model the 2 ways, and it wants to know how many photos there are. So those are my 3 answers to my 1 question here. Okay. Number 3. Draw an array, then write related equations to show the commutative property of multiplication. A page in Abdul's stamp book has 5 stamps in each row. There are 8 rows. How many stamps are on the page? So first we need to know how many rows there are. There are 8 rows, so we need to draw an array first. 1, 2, 3, 4, 5, 6, 7, 8. How many stamps are in each row? 5 stamps are in each row. 1, 2, 3, 4, 5. So now I'm going to fill in the blank spots, right? I need to make sure all my rows have 5 stamps. And I need to go all the way to 8 of them. 8 rows with 5 stamps in each row. I apologize, my allergies are acting up, so I keep sniffling. I apologize. Okay. So where my labels would be, I have 8 rows. And I have 5 stamps. Sorry. In each row. I'm sorry, I'm not writing very neatly. I apologize for that. So the multiplication equation that I could write for this array, or this model, would be 8 would be one of my factors and 5 would be the other factor. So I would write 8 times 5. So 8 times 5, well, I can count 5, 10, 15, 20, 25, 30, 35, 40. 8 times 5 equals 40. So what would the other equation be? Well, remember what we've been doing. We can just turn it in the other direction. So if I turn it in the other direction, how many rows do I have? I hope you're thinking 5. And how many stamps in each row? I hope you said 8. Right? We're just going to switch the factors around. So I'm going to say 5 times 8, and it also equals 40. So we're going to write the unknown factor. So we know that 8 and a 7 are factors. So that means 7 times, if 8 times 7, then that equals 7 times 8, right? Because the commutative property means you can just flip-flop them. Flip-flop your factors. 4 times 10 equals 10 times 4. Flip-flop those factors. All right, so what I would like you to do is your black and white worksheet. That's lesson 1.4. And after you finish the front and back of that, please either have someone at home take a picture of the front and the back, and you can either text it to me or email it to me or attach it on to Google Classroom, or you could just send it back to me to school. Okay? I hope you all have a great rest of your day, and I will see you for lesson 5 when you're ready to do that lesson. All right. Thank you. Have a great rest of your day. Bye.